Hello. Today we're going to talk about extended work energy principle. And we're going to apply this to a spring mass system. So we're going to apply this principle to a spring mass system with friction. So this is just one place you can apply this. So extended work energy principle says the following. So the work done by non-conservative, so this C is conservative. So the example of this is friction, apply force, tension. Okay. So the conservative force is those three, right? So just repeat it here. Conservative force is the gravitational force, electric force, and the spring force. Okay, so those three are the example of conservative force. So this is equal to the delta, so it means the change, final minus initial, of potential energy, plus the change, the delta of kinetic energy, final minus initial. So that is the extended work energy principle when you have work done by non-conservative force. So this is when you want to apply this law. And there's also potential energy change and kinetic energy change. So that's where you want to apply. So basically, it says that mechanical energy, right, ME, mechanical energy, is no longer, the change of that is no longer zero, right? So these two together is the delta of mechanical energy. Also means the mechanical energy is no longer constant. So the mechanical energy is not conserved. Sorry, mechanical energy not conserved. Okay, so part of it, it's been dissipated, right? And the obvious example is friction. It's been dissipated by the friction. Okay, so that's one example. So we're going to try to apply that to a spring mass system. So I'm going to change in color. So if you have a spring and mass, draw it. This is kind of like the wall, and that's the ground. And then you have a spring. Okay, and you already compress. And right now it's compressed. 压缩, okay? In Chinese, this means 压缩. Okay? So the regional nominal spring length is right there. See, it's right here. Right? So this is your nominal location. All uncompressed. Right? So then you have compressed this much. You have compressed this way, and that's your delta X. Right? That's your compression amount. Right? So that's called compression. Okay? And let's say you started from here. That's your position 1. Okay? And you let go. Right? But there's a friction here. There's a friction from here to here. Friction. Okay? So let's say the M is equal to 1 kilogram. So the normal force is equal to 10 Newton. Right? And let's say the friction coefficient mu is equal to 0.1. So then the friction, kinetic friction, is equal to 1 Newton. Right? Okay. So now the initial, right? So let's say the delta X here is equal to 1 meter, for example. Okay. And the K for this, the spring constant K is equal to, say, 100 Newton per meter. Okay. Right. So now, what the original potential energy, right? original, right? Original, which is equal to 1/2 K delta X squared, right? And that's actually, this is the energy total, right, of the system, initial, right? This is your initial total energy. So that's equal to 1/2 times 100 times 1 square. So that's equal to 50 joule, right? 50 joule, right? So when it comes to here, right, this location here, the KE. So right here, delta X is 0, right? Right there, delta X is 0. So the energy, it's in the kinetic energy now, right? So the kinetic energy at that location, right, it's going to be the potential energy, right, minus the work done by the friction, right, which is the work done by the non-conservative force. Right? Okay, so let's compute that. I'm changing color to this one here. So the kinetic energy will be equal to 50 joule minus work done by that. So it's friction, right? So friction is going this way, and the delta X is going this way, right? So we know this is going to be cosine 180, right? So minus, so that minus is coming from the cosine 180. So this one minus that, it's what's the remaining of the kinetic energy, right? So then we have 50 minus friction is equal to 1, distance 1, so minus 1. So it's 49, right? 49 joule left. So then you can go figure out what's the velocity and so on, right? So now you can see what did we apply. What we actually apply, I'm going to try to erase this and give you the kind of the summary here. So what we apply is work done by the non-conservative force is equal to the delta PE plus delta KE, right? Which is the extended, right? Extended work energy principle, okay? And this is equal to the potential energy in the end, right? Final minus potential energy initial plus this one here, kinetic energy final minus kinetic energy, right? Initial, right? So a few terms that we can get rid of, right? So this one, initial is 0 because we have the compression and the thing is starting from rest. So that's 0. And the potential energy final is 0 because when it comes from, when it comes to the location where it's nominal, right? The delta X is 0. So that's equal to 0. So this one here was the 50, right? So that's equal to minus 50. And this one here was the 49, right? Plus the 49, okay? And that's equal to your W and C, right? So that's what we applied. And actually what we did was this, okay? So then this is equal to minus 1, and that's equal to your F times D, and then times cosine 180, right? And this is negative 1, this is 1, this is 1. All right? So that's all we have for the day. Extended work energy principle applied to a spring mass system. Okay? Hope you enjoy that. And